To close out our discussion of foundation design and also our sort of tracking through of structural elements in buildings, we'll finish with foundation types. And we'll do one quick example to show how we calculate and how we decide what type of foundation we're going to use and how deep that foundation needs to be, or more accurately, on what level of soil or strata that foundation needs to be. We'll do this in sort of two scales. We'll look first at low and mid-rise, and then later on we'll look at high-rise construction and the sort of more exotic foundation types that we use for skyscrapers. If we're putting a one-story building on the ground, do a little thought experiment, you can stack most of the things that would go into a building, people, furniture, boxes. If you just put those outside on your front yard, the soil will support them. And so if we have a one-story building, our foundations can be really simple. All we're trying to do basically is take our live loads, the dead load of the building, and put it on top of a soil stratum that can handle it. We might scrape off some of the really loose soil. We might try to find soil that's a little bit more compact, something that's more like a clay. But a single story building, we can usually get away with what's called a slab on grade, right? Just simply scraping off the top layer of soil, pouring a concrete pad, leveling it out, and then putting our building on top of that. In cold climates like the Midwest, we might want to go deep so that we get below the frost line. We don't have to worry so much about frost heaves. But so long as the whole building is on the same stratum, it may not be necessary, right? The building may ride up and down as a whole with a frost heave. It's only if we have different sort of elements or different heights, different levels of foundations that we're worried about really getting below the frost line. As we get bigger and bigger, though, as we pile stories on top of one another, eventually we find that we can't just put the kind of dead load and also the kind of live loads of the building onto whatever soil we've got. We have to actually dig down and we have to find a stratum of soil that can handle those loads. And we often find that we need also to spread those loads out. So to actually do the exact opposite of a slab and take the point load from a column or the linear load from a wall and put it on a footing, right? Actually increase the area, the bearing area that the building has on a stratum of soil. We can do that in a couple of ways. We can basically take what we call a mat or a raft foundation. If we have good soil that's relatively close to the surface, we may just be able to build a super strong slab, one that can take the bending and shear loads of walls and columns coming down onto it, and literally just kind of float the whole building, right? Think of the building as a giant boat that is sitting on top of a good level of soil. Here you see that we're on gravel, which is relatively strong, has the advantage of draining really well, so we're not quite so worried about frost heaves. More frequently, though, we'll find that the loads from those walls want to come down onto what we call spread footings. And this may be because we are worried about building a really deep slab capable of resisting the shear and bending that we get with mat or raft foundations. It may also be that the soil isn't quite strong enough to handle the building just on its own. As you can see, we may need to take each one of those columns, each one of those walls, and give it its own little like lily pad, right? A little slab, inverted slab that takes the load of the column or the wall and spreads it out over an area of soil below us. So the simplest of these, again, is a slab on grade. If we are able to just basically take the live load, like in a house or maybe a big box store or something, what we'll typically do is we'll excavate a little bit. We might go below the frost line, or we might insulate the soil so that we're using the heat of the building to keep the slab warm. And then by insulating it, that slab is then going to radiate and warm the soil around it. It's going to prevent frost heaves from happening. We'll usually design the foundations of a slab on grade with a little bit of a perimeter beam to handle the loads of walls coming down onto them, also just to give some rigidity to the edge of the slab. We'll excavate and remediate, so we'll take off 5 or 6 inches of organic soil, and usually we'll put some kind of gravel base. And the gravel, first of all, is going to bear very well, so it's going to transmit loads equally to the soil below it. but also because it's porous, again, it's going to keep water away from just under the slab. And even if we're heating the slab, we may be a little bit concerned down the road if there's a long power outage or if the building is without heat for a while. We don't want any water there that's going to freeze and try to push up on the slab. Rebars in the edge beam, again, this is going to function in bending, and we'll usually put wire mesh or reinforcement in the slab just to take any local bending and shear loads and to keep the slab from cracking. So very, very simple. Very popular in warm climates, especially. Less popular here in the Midwest, where we are worried about cold soil, we are worried about frost heaves, and typically we're putting in a basement anyway for safety during tornadoes and bad weather. So this is something you see very frequently in the southern United States, less so in the Midwest, but something that does occasionally happen. Spread footings are much more common, and here what we're doing is we're excavating through poor soil levels, and we're getting down not all the way to the point usually where a column can just sit on the soil, right? We're not going all the way to bedrock, but we're trying basically to float the building on spread footings that are going to spread the load out over a fairly wide area of soil. So not overtaxing the soil, also not going down too deep. And it's usually a balancing act of how much excavation we want to do versus how large we want the footings to be. The way these work is that we always transform from steel, if we're using steel, into concrete. If the building structure is concrete anyway, then the concrete column can just come straight down through the ground. The steel column, of course, is vulnerable to corrosion and oxidation. So we try always to have at least a couple of inches of concrete above the soil level. Once we're below the soil, we're going to come down at least below the frost depth, but usually down to a stratum of soil that is like gravel or hardpan, something that can take a fairly high load in tons per square feet. We are going to then attach that column to the spread footing down here, and this is analogous to the slab in floor construction. So we're taking that point load and spreading it out over an area. We calculate that area, again, based on the allowable load per square foot. We know what the load of the column is going to be, or we can estimate it. We know what the bearing capacity of the soil can be. It's a simple division exercise to see the number of square feet we need to spread that load out over. That spread footing is going to have reinforcement in it because it's going to take a lot of shear, a lot of bending. And it may be that right around the column, we need to either make the spread footing a little bit deeper to handle this extra shear, or make the column a little bit wider, right? Bell the column out, add some geometry in here that's going to, again, maximize the interface between the column perimeter and the footing section. Underneath it, usually we'll have a layer of compacted gravel, again, to keep water away from the foundation, but also to ensure that we have a very broad bearing base below. And here you see under construction, this is the reinforcing cage for the spread footing. We have reinforcement usually in the concrete column to keep it from spalling or to handle any local bending. And you see that those rebar reinforcing bars in the column are turned out into the spread footing, which helps to handle the shear. And here again, this is the reinforcement that will go in the column, and you can see a little bit of the reinforcing cage in the spread footing down there. These are, we can sort of expand these spread footings to handle either columns, as we've just seen. If we sort of extrude that shape along the perimeter of the building, we get a linear spread footing. So this is what we would put underneath a bearing wall, for example. And here that bearing wall is going to act essentially like a beam, and it's going to often bridge soil that may have slightly different bearing capacity. We want that very, very large beam to be monolithic so that it can take any of that differential settlement that might happen otherwise. Now, the question of the area versus depth is one that's got a long history to it. And in the 19th century, the kind of earliest skyscrapers that were built out east were built in a couple of cities, New York, Boston, that had bedrock very close to the surface. So spread footings could be built very easily, usually bearing wall construction in early skyscrapers. So underneath the bearing wall, they scrape off a few feet of organic soil. In lower Manhattan, bedrock is literally right there, just a couple of feet below the surface. And so they would build little kind of feet on the bottom of bearing walls, mostly for stability. But that, of course, spreads the load of the bearing wall out over, in this case, a very, very strong soil stratum, right, bedrock. The spread footing there is mostly for stability, right, to keep the wall upright. In cities like Philadelphia and Chicago, river cities especially, it was a very different condition. Chicago downtown has about 80 feet of basically fluid soil, clay, hard pan down 20 feet or so, but fairly weak soil. And so what happened in Chicago is they realized that they essentially had to float the buildings. And they really came up with the science of spread footings, first using stone pyramids. And then once the steel and iron industry began making rails in the city, using what were called grillage footings, basically grills of steel I-beams that could act literally as reverse slabs, handle the kind of immense shear that some of these columns were beginning to put onto the foundations. These were good in Chicago because for calculation purposes, they didn't like walls. Because the wall could again go over several different types of soil, you never quite knew what was underneath it. They wanted to limit differential settlement. And so they could calculate, they could confirm the soil underneath a single column much easier. They could do more simple calculations for that. And so they tended to use columns instead of walls, whereas New York and Boston used walls. Finally, in 1894, building engineers started using techniques borrowed from bridge design. And now with super tall buildings, we use what are called caissons. So these are literally tubes that are drilled down through the poor soil all the way to bedrock and then filled in with concrete to basically provide very, very long mega columns underneath the soil that take the load from skyscrapers above and transfer them all the way to bedrock. This is the difference between basically floating buildings on poor soil and just making the loads of the building bypass all of that poor soil. And with relatively narrow columns compared with grillage footings, finding a way to get through all of the junky soil to rest directly on bedrock. What does that look like in 3D? Well, this is a typical spread footing under a bearing wall. So the wall is here. There's maybe a shear panel here to, again, increase the interface between the wall and the footing. And then here's the depth of the spread footing here. So that load is basically getting spread over a slightly wider area of soil below. Those stone pyramids were designed basically to spread the load out. And in stone, they're worried, of course, about shear. If you build just a flat floor of stone, a column is going to go right through it. So they would build pyramids to literally take the shear from the column and spread it out over successive terraces of stone. The advantage to the grillage foundations is that you basically bought space in the basement. The grillages were much lighter. They put less dead load onto the soil themselves, but you open up the possibility for basements below. And as you can see, by layering the I-beams up, you get this multi-directional resistance that we talked about in slab design, right? These are basically two-way slab foundations. The load path is just exactly the opposite from the floor slabs that we were looking at in the first couple of lectures. Here, this is what strip foundations or shallow foundations look like today. We do these a lot now for houses where we'll dig a trench. We'll put down a kind of wide strip foundation. Again, in a house, they don't need to be very big because the soil can hold nearly the weight of the house just on its own. And then the same principles apply. We go below the frost depth, 48 inches in most of the Midwest. We have rebar in the strip foundation because this is going to experience bending, especially have differences in soil as we go along. And we may have a shear panel as well, right? So there may be a couple of steps in here to get the loads from the wall transferred successfully into the strip foundation below. And again, we're usually putting it on compacted gravel. so that there's an opportunity for drainage around the foundation. Now that is slightly different from retaining walls, which are another kind of foundation. When we're putting bearing walls underground, especially for building basements, we're worried about the lateral pressure that the soil imparts to those walls. And so in addition to designing them for compression and shear, trying to get the loads straight down into the soil, we typically also have to design foundation walls in bending, knowing that the pressure of the soil is going to try to both slide the wall over and tip the wall over. If we're just going below the frost line, we might have what's called a gravity wall. So this is a wall where you can see the pressure of the soil building up here. It's trying to push this wall counterclockwise. And usually, just with a thick enough wall, we can counteract that moment. We may batter the wall a little bit to give it a little bit of an extra foot down below. If we're going deep, a story or more, we might do what's called a cantilever wall. So we might take advantage of a basement slab. We might thicken that slab as it comes closer to the wall. We might put what's called a key underneath the wall that not only helps us with the shear that wall is going to impart to our foundation, but also provides some resistance, right? It pushes against the soil below in the opposite direction as the soil above it is pushing the wall. So the soil above the wall is trying to put a counterclockwise moment into our foundation. The key and also this kind of cantilever here pushing against the soil are providing a resisting moment that goes in the clockwise direction. And this is going to keep the wall stable. And then finally, if we're going really deep, we may have to put a sort of double cantilever where we have another sort of beam or slab here that's actually using the weight of the soil pushing down to resist the weight of the force of the soil pushing over. And this, of course, is going to give us a very, very broad set of feet that are going to stabilize the wall, give it much more stability than a cantilever or just gravity. We can, in mid-rise buildings, also just simply build a very large foundation under the building called a mat foundation that ties all of the columns and all of the walls, all the bearing walls in the building together at the lowest level. This mat foundation is going to basically equalize the pressure on the soil all over the site. So we get the building is going to want to settle consistently no matter what the conditions of soil are. The downside is that the slab is now experiencing shear at every one of those columns and bending between them, right? This is literally a reverse floor slab, only now we have the punching shear problem at every column because the whole weight of the building or the whole weight of the height of the building is coming down on each of those columns and giving us really a worst case shear where we're trying to collect all of those loads and spread them out over the soil. So mat foundations are often quite deep to resist this, or they have to come with basically a grid of beams on the top or bottom of them. And again, that helps spread the shear out, but it also gives the mat some considerable strength in bending. And again, note in like more than one direction, right? This is a two-way slab. It's just the load path is reversed. We're going from point load to a distributed load in two directions. The fun really begins when we get into high rises and we get to the point where we have a building that is so heavy that it can't possibly be supported on any of the soil that we've got underneath us. We've got to find a way either to get down to rock or to trick the soil into supporting our building for us. The most direct way to do this is with caissons. So with caissons, as I said a minute ago, we're taking the loads of the building through very, very long columns all the way down to bedrock. And you can see here we've got basically a drilled shaft. We send tubes down with a drill bit in the middle. It literally just scoops out the muck. The tube prevents the soil from collapsing in on itself. At the bottom, very often, we'll have what's called a bell. So we'll send a very special blade down that actually expands, drills out a conical volume and then a cylindrical volume below that. And this acts basically like a spread footing at depth. So that can be maybe 80 or 100 feet down below the surface if we have a lot of poor soil, as we would in Chicago or New Orleans or a lot of coastal cities. Once that is all drilled, concrete gets poured along with usually a rebar cage, and we get this very, very long, skinny column that then can support the building structure from the lowest level on up. There'll be a column cap there that takes the column, makes sure that it's centered on the caisson, and then the caisson will take the load all the way down to bedrock. Now, you may be asking yourself, well, if this is a 100-foot long column, that seems like it violates everything we've just learned about slenderness ratios. And the advantage is that the worse the soil is, the better the caisson is going to behave, because as we get down below 10, 20, 30 feet, that caisson is going to experience not only the vertical load of the building, but it's going to experience lateral loads in every direction from the hydrostatic pressure of the soil. Right? And the more the soil works like a fluid, the tighter its grip is going to be, the more it's going to stabilize the column, prevent it from buckling in any one direction. So caissons, even though they require an awful lot of very careful, very painstaking excavation at the very beginning of the project, these allow us to put the full weight of a skyscraper all the way onto bedrock, no matter how far the bedrock is below the surface. We have a similar looking system, but a very different mechanical system in what are called friction piles. We might use these if we've got bedrock that is way, way down, like more than 100 feet below the surface. Or we might use it if we calculate that we can take advantage of the liquid soil to have this hydrostatic pressure, not now laterally, but vertically. What do I mean by that? Well, if you take like a broomstick to a beach, right, and start to drive the broomstick into the sand is a relatively fluid soil, right? It's not a great foundation. If you put a mat foundation on sand and shake it around, you'll be able to move that through the sand eventually. If you take the broomstick and start to push it into the sand, what you find is that the friction of the sand around the surface of the broomstick starts to build up, and the further the broomstick goes into the sand, the more interaction you have between the surface of the broomstick and the sand around it. Eventually that friction builds up to the point that you couldn't push the broomstick into the sand anymore. This is what we call a friction pile. And when we use these to support buildings, we'll pound clusters of piles, sometimes timber, more commonly now precast concrete or steel. We'll pound those piles into soil, very often liquid soil, until we get to a point where we see the pile putting up enough resistance that we can rely on it. And once we know how much each pile can support, we can add 10 or 20 piles. We can pour what's called a column cap on top of those, and we can center a building column over the column cap. And the friction working on all of those piles, sometimes in a large building, it might be hundreds of piles, the friction of the soil around those piles will actually hold the building up. This is often the case in buildings that are on riverfronts or coastal buildings. They are resting not on any form of bedrock, but actually they are literally like suspended in this liquid soil by friction piles. And this is showing often very deep column caps because you do get big shear loads here, right? This ends up working like a distributed load, fairly discrete distributed load, but nevertheless, you can think of this as a distributed resistance. And here we have the point load, and you can imagine that that's going to give us a fair amount of shear. Finally, we can, the other way to do this doesn't work for super big high rises, but for relatively low ones, we can do floating mat foundations. And if we have very liquid soil and we have a fairly broad footprint, we can actually design the basement like a boat and literally float the building in a fluid soil. This often requires stabilizers to prevent the building from moving laterally, but we're relying on the displacement of a fairly large basement to literally float the building, to make the sum total of the building weights less than the weight of the displaced fluid soil, literally floating it using Archimedean principles. Pretty rare, but possible. And again, the worse the soil, the more fluid the soil, the more likely this is to actually work, right? Because it's going to behave more and more like a boat and less like a spread footing. So here's a piling operations at a couple of different scales. This is a pile driver at a sort of residential scale. And you can imagine that hammer driving that timber pile in, and eventually our intuition tells us it's not going to go any further. And that's not because it's hitting strong soil below it. It's because the fluid nature of the soil around it is providing enough friction to resist the vertical load that we're putting on it. This is what a piling operation looks like in a maritime environment. And you can see we've got a pile driver here on a float, and that pile driver is going around jamming these concrete piles into what is probably very poor soil, right? There's going to be a zone of water and then a zone of liquefied soil, and that liquefied soil is what they're going to have to rely on for the friction fit. Here's a similar case. This is a pile driver, and you can see that the science behind it is really simple. There's a giant weight that gets lifted up and dropped, and every time it drops, it pushes that pile further and further into the soil. Eventually, every time they drop the weight, the pile won't move, and that's when they say that it's hit its total refusal, is what they call it, and they can rely on it then to provide a fairly robust resistance to loading above. This is resisting a dynamic load. All we're asking it to do during its lifetime is resist a static load. And we do occasionally use piles that are called end bearing. So if we have a decent stratum of soil below us, we can certainly rely on that as long as we have enough surface area of piles to rest on it. More often, we're relying on the side friction, the friction along the pile, or some combination, right? The bearing capacity of the ends plus the friction capacity of the surfaces. Compaction piles, what we're doing is we're driving the piles literally to push the soil together, right? To drive the soil out of the way and to densify it. And this is one way we have to remediate the soil. So you may see a pile driver out there for 3 or 4 different reasons. Usually, though, friction piles, especially if you see one in a riverfront construction site, they're usually driving piles that are going to be friction piles. So how do we size foundations? We take the tributary area, we use the same process that we use for column loads. We take the load usually on that last column, right down at the first floor, and we get what the total load on the foundation is going to be. We get the soil survey from our geotechnical engineer. We go through and we can figure out what the size of the footing is going to have to be at each stratum, right? So we're going to need a very big one if we want to rest the building on organics, a slightly smaller one if we want to rest it on clay. By the time we get down to bedrock, we need relatively small ones, and that's the logic behind a caisson. Deeper generally goes smaller, and at some point we get to the point where we can actually rest the building on relatively small drilled columns instead of on spread footings. And depending on the local cost of excavation, depending on the conditions on the site, we're going to choose a foundation system and a foundation depth that are going to negotiate between the size of the footing we want to build and the depth of excavation we can afford. So what does this look like? Well, we'll get a geotechnical report that'll tell us fairly accurately where the different strata of soil are. So here we've got a tall building. We've got our 900 square foot bay, 30 feet by 30 feet. And we can calculate the tributary area. And then our geotechnical survey is telling us that we've got medium silt for a meter. That's a bummer because that's a terrible soil. Hard clay for 2 meters, much better soil. And then 10 meters, about 30 feet of compact gravel. So just 13 meters down to sound rock. But we would like to find the kind of simplest foundation system that we could. If we could put the building on medium silt, we would love to do that. odds are we're going to have to go at least to clay or gravel to get a decently small foundation size. So we will go with the worst case scenario, so a full bay area of 900 square feet. The edge column will only be carrying 450. The corner columns will only be carrying 225. But we'll start with the worst case. So if the loading for each floor is 100 pounds per square foot, largest bay area is 900 square feet, what we find is that the 20 stories times 100 square meters times 100 pounds per square foot ends up putting 1,800,000 pounds onto each column at the base. And that, if we divide by 2,000, gives us 900 tons. And civil engineers are generally working in tons. So our bearing capacity is going to be measured usually in tons per square feet. So we will take from our chart the allowable load per square foot of soil. So medium silt is 1.5, hard clay 5, compact gravel 8, and then sound rock all the way up to 60. The total load on each one of these is always going to be the same. So the worst case is 900 tons, 900 tons, 900 tons. And all we do is we divide the load that we're putting onto the foundation by the allowable load in tons per square foot. And that will give us a required square footage for the foundation itself. So here you can see on medium silt, we could actually make a foundation, right? This is smaller than the 900 square feet per base size. The issue there is going to be shear. We're putting all of that tonnage onto a relatively small mat foundation, and the column is going to try to punch through that foundation, right? Knitting needle through a birthday cake. So that is possible, but not really realistic, right? That's a huge foundation size. Now, if we go to hard clay, we find that the foundation size for a spread footing is only 215 square feet, or about 15 by 15. That's certainly doable, and it means that we only have to dig pits that are 15 feet square, plus a little bit to get down there and get the formwork installed. If we're willing to go down a little further, that next 3 meters, we find that compact gravel with an allowable load of 8 tons per square foot only requires 134 square feet of foundations, or 12 foot by 12 foot. Somewhere in there, one of those two is going to be more economical, depending on labor costs, depending on how much it costs to excavate. We may find that we want to go down less far, but provide more area, or we might dig down further and use less material for the foundations. The other big decision, though, is going to be whether we want to go all the way down to sound rock. If we do that, if we go all the way down that 13 meters to bedrock, we find that we only need 18 square feet, right, or just over 4 by 4 to hold up that 900-ton load. And that's in the realm of drillability, for lack of a better term, right? That could be a cylinder that's the equivalent of 18 square feet, or it could be that we drill a relatively smaller caisson, maybe 2 feet in diameter, and then have a bell at the bottom that gives us a bigger foot on the bedrock. That might be a more economical solution than hiring labor to dig all of this soil and to remove it, to put it somewhere else, hopefully on the site. These are the sorts of figures where when we do the calculation, total load divided by the allowable load per square foot on the soil, when we get into the kind of low double digits for required square footage, this is where we often see caissons come into play. Okay, to finish up, I want to tell you a really good story about foundations. And it has to do with one of our favorite buildings in SciTech, the John Hancock Center in Chicago. We talk about this for all kinds of reasons. When we talk about frames in the next class, we'll come back to the Hancock Center and talk about its superstructure, what's above the ground. But the Hancock also has a really, really interesting story that happened below ground. As the building was being built, a 100-story tall building, right? Going to be the tallest building, not only in Chicago, but one of the tallest buildings in the world when it's done. In the summer of 1966, they had gotten up about 7 or 8 stories, so a little bit before what you see here. They had the steel framing up. They had dug caissons. They were putting the steel framing up. And a workman showing up on the job site in August 1966 noticed something terrifying. So let's set this up. The first thing that they do is they drill caissons. They send tubes down into the ground with drills inside of them. The drills remove the soil, and then the tube excludes the soil, prevents the caisson or the void from collapsing. They put rebar in, they throw concrete into it and let the concrete cure. Then they put the steel columns onto the caisson foundations and start to build the framing, right, as they go up. And it was about when they got to the 7th or 8th floor that a workman showing up in August noticed that around one of the columns, the floors were all sloping toward the column. What had happened was that clearly one of the caissons had failed and it had dropped a few inches, meaning that all of the structure around that column on each of the floors was now sloped, right, heading toward the column. The contractor, to their great credit, called the structural engineers at Skidmore, Owings & Merrill. So we think you should come out and see this. Fazler Khan, great Chicago engineer, comes out and he says, we've got to stop construction. Something's happened underground. The caisson isn't carrying the load that we thought it would. We're only at floor 7 or 8. Imagine what would happen if we got the whole building framed and one of the caissons collapsed, right? That whole column bay could come down. Not to mention that even if the column survived or the caisson survived, all of those slanted floors would have to get either certainly replaced, and they might not be serviceable, right? There might be a greater slope than we could stand to make the building work. So construction stops for 6 months. They investigate what's happened by taking sample cores, drilling into every one of the caissons, and confirming that the caisson is either solid all the way through or not. In the broken caisson, what they discovered was that the caisson had somehow split, and liquid soil had rushed in to fill the void, and the caisson had collapsed. And going back into the job site communication, they figured out what had happened. The contractor had wanted to save money by reusing the caisson forms, by taking the tubes out after the caissons had cured. So remember, we're drilling down, we're making a void in the soil. There is a steel tube that's keeping the soil out. And what the contractor proposed was that after filling up those tubes, they wanted to pull the tubes out. Once the concrete had cured, it would pull the tubes out. Now, this can be done. It means that you have to put a form release on the inside of the tubes, basically lubricating the inside of the tubes so that they don't stick to the columns. What had happened was they hadn't done a great job of lubricating the tubes, and in fact had tried to pull the tubes too quickly. And when they did that, it pulled the upper half of the caisson with it. And that split the caisson, pulled that caisson not completely out of the ground, just a few inches. And the soil then rushed in. It was able to sustain the load of the first couple of floors, but eventually not when the structure got to 7 or 8 stories. For 6 months, they tested each of the caissons. They built a new caisson around the one that was damaged. They reframed that column bay and continued along with the construction. You can read the whole story here. 1985, the Chicago Tribune ran an article on the foundation failure and the way it was actually solved. Building ended up going up fine, right? Great masterpiece of structural engineering, structural architecture. The original developer, however, went bankrupt. The 6 months that the building was delayed ended up bankrupting the developer. The Hancock Insurance Company, which had originally just planned on being a tenant, ended up taking the project over and attaching their name to it. So here is an example, even though we think of foundations as being hidden away, underground, maybe a little bit dull, here is a case where foundations changed, if not the skyline of a major American city, at least what we call the buildings that are in it. Okay, we'll have one final structures lecture for 347. It'll be a review. It'll be one lecture where we pull together all of the charts, all of the processes for designing slabs, beams, columns, foundations. That will be one kind of handy place that you can go when you do the final project, which will ask you to size each one of these in a building framework.